Okay, so let's start this colloquium. And first, I will give you a brief introduction to our speaker, Nadejda Blagorodnova, who recently was awarded with the Talent Jove research, how it's called. I have forgotten the name of the prize.
Well, it's Youth Talent Prize, yeah,
Youth
Fundació
Talent.
Catalana de la Recerca.
Això mateix, gràcies. And we thought that it was a good idea to ask her to give us a colloquium on her research, taking profit of this opportunity. And well, so let's start with this brief introduction. Dr. Nadejda Blagorodnova got a degree in computer engineering at the UPC Facultat Informàtica de Barcelona, and started to work with Gaia as a software engineer, where decided to pursue a career in astrophysics. So she started a master here at the UB, the master's degree in Master de Física de Partícules, Astrofísica y Cosmologia, I think. She carried out her PhD at the University of Cambridge in the UK. She got her PhD in 2015, I think, where she was working on the discovery and characterization of optical transients using the daily stream of Gaia data. Nadejda carried out her first postdoc at Caltech in the US from 15 to 18, if I remember correctly, working on tidal disruption events, the development of a low-resolution spectrograph, and stellar mergers. From there, she moved to her second postdoc at Radboud University in the Netherlands with a Veni fellowship and continued working on stellar mergers. And in 2021, Nadejda got an ERC starting grant for her project CT3PO, studying common envelope transients. She started to work at the UB in October 2022 as an investigadora distingida and became professor agregada in November, associate professor in November 2023. Presently, Nadejda represents the area of stellar physics research at the ICCUB and is a member of the Institute Governance Board as a scientific secretary. And well, after this brief introduction, please, Nadejda.
Yeah, thank you, Valentin, for the introduction, and thank you all for being here today. I'm excited, to share the research that we are doing with the group here at the ICC. So first of all, the title of my talk is Illuminating Binary Evolution with Luminous Red Novae, their progenitors, and their dusty aftermath. So what this means is that we're going to use a certain type of astrophysical transients as tool to better understand stellar and, in particular, binary evolution. So why do we care about stars? Well, first of all, stars are the building blocks of our universe. And if we want to understand how our universe works, we need to understand these little bricks that make our galaxies and the galaxies that make our universe. Stars are responsible also for the evolution of the universe. For example, its chemical enrichment. They make heavier elements in their interiors. They're also, when they explode, for example, they're sources of high energy particles or highly UV ionizing particles. And also when they shed, let's say, these heavier elements, they can enrich the interstellar medium with heavier components and make dust. But yeah, this picture is very simplistic because in each brick we see one star. So I would like to tell you that this picture is outdated. So when we look at the universe, we should look something more like that, right? The universe likes to dance in pairs. So the bricks are rather like kind of stars which have companions, and these companions have a very large influence in all these three fields as well. Some of the binary change the chemical enrichment of the universe. They also, stripped cores of stars also can enhance the UV radiation, which was especially important at early times in the universe to fully ionize it. And also binaries enhance the composition of the interstellar medium. Here I would address how these transients can help us understand all this. So first of all, let me go to the example of nucleosynthesis. So here we can see the abundances of different elements compared to silicon. This is the mass number of the elements. So if we look at this diagram, we can start identifying, for example, some familiar elements such as hydrogen and oxygen that make water that we need to make life, and also certain elements such as carbon, nitrogen, and oxygen that make most of our bodies. So these are elements are here. Then let's proceed. We can identify calcium that makes our bones, or also here the peak is the iron that makes our blood. So we have all these components in our cells already. So if we go a little further down the mass number, we can start identifying, for example, nickel that together with iron makes the core, our planet, the planet where we are living. So this is a very important composition. And finally, down the road, we have the very heavy elements, which are these precious metals of gold and platinum that some of us like to wear in like special occasions, such as weddings, for example. So these elements are present in our daily lives, and we are very familiar with them. But then we can ask ourselves, where do they come from? And what is the role of different physical processes? So here, for example, we have that the Big Bang was responsible for only the lighter elements such as hydrogen and helium, a little bit of lithium. But then the massive stars, like larger than 8 solar masses, were responsible for burning, right, like these elements in their stellar interiors until reaching the iron core that in these cases collapse. So this is a problem. We make a lot of iron, but then the stars collapse their iron cores in the neutron stars or black holes. So most of this iron, it actually gets locked into these stellar cores. So yeah, that's not there. So then we also can look at the envelopes of low mass stars. So stars lower than 8 solar masses, they live kind of long times, and they generate through several processes. For example, an excess of neutrons that can, by slow kind of nucleation process, they can aggregate into like some kind of pre-existing iron particles, and they can grow in mass. So they can generate these kind of heavier elements. But then this is single stars, and that's it. If we want to have any companions in our life, we will be missing our blood, and we will be missing our golden rings. So, where do these elements then come from? Well, ladies and gentlemen, we need binaries. I guess you guessed that's my topic of favorite research. And for example, the iron, or most of the iron that we have right now, comes from supernova that form from 2 low mass stars. So these ones that were creating these S-process elements also left stellar corpse, which has carbon-oxygen white dwarfs, that when they merged, they created type 1 supernova. And finally, here also kind of heavier elements that we need actually neutron stars. So this is our corpses of like massive stars that kind of were dancing together within our universe, Hubble time, until they, through emission of gravitational waves, they got actually decayed, and they generated a neutron star merger, which created all these heavy elements. So basically, even in our cells and in our daily life, we need binaries to actually understand, for example, nucleosynthesis. So how do we find these binaries? Where do they come from? So the first idea is that actually most, if not all, stars already are kind of born in groups of binaries or multiple systems. So here would be the initial stellar population. This is the binary diffraction and the kind of the more massive star mass. And the idea would be that all stars are actually born in a large family, with brothers and sisters. But then what happens? Like with time, and especially dynamical evolution, we believe that they are losing a part of these companions. So imagine you are going to Plaza Catalunya, like today with your friends, a bunch of friends, and you want to get to the other side. And there's it's massive, it's full of people, right? So if you make 2 steps, you're very likely to remain with your group. But if you cross the whole square and it's full of people, likely by the time you reach the other side of Plaza Catalunya, you have half of your friends missing because they got sidetracked, like taking pictures or doing something or bumping into somebody. So this is a bit the idea that we have here. Because if we look at the lives of these stars, like the more massive stars, they live very little. So it's just very few million years compared of thousands of million years of these guys. And for reference, this is a galactic year. It's like kind of the length when a star takes to give a round into our galaxy. So basically these stars, they're born in a big family. They say, well, I'm born. They make a step, boom, they're dead. you know. But these guys, they have time. They go round and round and round and round, right? So they're like the probability of losing their siblings is much larger. All right, but this is not so bad. This is our sun, one solar mass. I mean, it's still like half of stars like our sun actually still have a companion. And if we go to a more massive system, there like the companionship increases. But then, I mean, we not only want to have companions, we want them to do something with them, right? This works. No. Yes. So then what we should look is at the distribution of where the companion is. So here we have, again, like a fraction of stars for different masses, low mass, our sun, 3, 10, and 30. And here we can see a log period distribution. And this is a line that says will interact. Okay, so basically anything which is shorter period than this line will interact, and if it's longer, it will not interact. So if we care, let's say, about massive stars, the ones that make neutron stars, that can make gravitational waves, and we are all excited about. So let's look at this line. The thin line is the inner binary, and because there may be more companions, you have this one. But yeah, the inner binaries for 10 and 30 solar masses, most of them, they're in this region that says will interact. But then this period is like, well, this is already like what, 100,000 of days. So I mean, they will interact, but then we said we want them to make these stellar corpses that are so close together that gravitational waves take, like part of this angular momentum, and they merge in a Hubble time. But they are like thousands of days apart. So how do we get two stars that are born apart through interaction into a much closer orbit? I think I should go to the other side. All right. So let's focus on the massive star case. So we have with two stars, generally one will be more massive than the other, like at 0 main sequence, and then it will start interacting first. So it will start transferring mass into its companion, and then this process, which we'll explain a little bit later, can be, for example, stable. Stable means that the system kind of never becomes, never the mass ratio gets very high, so they just strip each other. And for example, this star will end up being a UV bright source. So look at this temperature. This is 60, 50, 80, 70 kilokelvins, right? So this is like super hot, stripped cores of stars. They are responsible for huge amounts of UV radiation, and basically they have been only discovered very recently, like this is 2023, because they were not detected in the optical. They were like kind of missed in all the optical surveys. And now we know that they do exist, right? So by stripping, you can enhance UV, and that would have been very important in the early time universe to generate all this ionizing radiation. So if the mass transfer is unstable because it's become extremely high, what we can happen is it's a common evolution where the companion will actually enter, say, the envelope of the other star and start like stirring this gas inside. So then, in one case, if only part of this outer layer of this envelope is ejected, we will have a stellar merger. So basically, the new star will become a more massive and likely rejuvenated star because it will have some extra hydrogen in its core to extend its life. So these stars are also known as like kind of blue stragglers, if you know these clusters, which are stars that are like too massive and too young to be there because they were all born at the same time. It's like, what are you doing? You should be dead. Anyway. So if the mass transfer is unstable and we manage to eject all the envelope, basically, as you see, this spiraling actually brings the companion much closer to the core of the donor star, right? So they are already ended up in very close configuration, and because they are massive stars and their evolution is kind of more kind of driven by the core mass, this star will explode as a core collapse supernova first, and it may generate a neutron star. So then we can kind of repeat the process again. This star evolves, transfer mass, we can undergo common envelope, can also derive in a merger or in a tighter configuration, and then this star can become a core collapse supernova. And then they can merge, generating gravitational wave source and all this nucleosynthesis that we need. Meaning this is for isolated binary scenario. We also can make gravitational sources through dynamical interactions. And we have, for example, Mark's group at the Institute doing that. But I'm focusing on, let's say, just isolated binaries. All right, so yeah, we see that it's a long path. And if you want to understand something that it's at the end of the long path, you should understand every single step, right? And this is a problem, because actually right now we have huge uncertainties into several of these steps. We don't even know like which stars follow this path and which follow this path. How stable is mass transfer? This is an active field of research. We want to know which binary pairs follow here, this arrow, which ones are going down this channel. Common envelope. Wow, it's amazing. We need it. We know we need it, but we don't understand it really well. It's like one of the most important kind of probably steps in binary astrophysics, and we don't understand it. Right? So like understanding how and how much of the envelope is ejected will tell us how many stars are following this path and they become mergers and stragglers and so on, and how many will actually become a tighter pair. And the same for here. So basically, because we don't know how these paths occur, there's like huge like factor of 3, like order of magnitude uncertainties on the rates of this channel, right? We still don't know. Every time we add uncertainties, and at the end we don't know anything basically. So what should we do? Like, are we hopeless? Well, I hope to show that we are not. So we have observations to shed light on some of these very unknown processes. So one important thing is that when we have this stirring of the envelope by the companion, we know that this process can eject part of this envelope. And we believe that we understand how this happens. And we have discovered that there is an astrophysical transient that actually is doing that. We can detect them through, repeatedly surveying the night sky with ground-based telescopes. These transients are called luminous red Novae transients. I mean, the red part is very obvious. I will explain the luminous part. So when we see one of these transients, okay, that was a ejection of, maybe partial, maybe complete common envelope. But what else can we learn from this? Well, we are lucky that every time more and more we have more complete and higher quality and deeper archives. So we can go back to these archives and look what was there. In this case, we can see there was like this yellow, beautiful star at the location. So then we can actually study the properties of the star and understand better what was there before. Or we can wait a few years and then reobserve this remnant with different facilities to understand what's left behind, what kind of star it is, and what kind of dust it's forming, for example, and how it can contribute to this interstellar medium. So these luminous red nova sit here. They're called luminous because novae are here, and luminous red nova are more luminous than a nova, but basically they're fainter than supernova, core collapse, thermonuclear, right? These are here on the top. Normal novae, like this is an explosion on the surface of a white dwarf. So they are like in the bottom. So they belong to this kind of gap transients, so-called, which are in this luminosity gap between supernovae and novae. But as you can see, they are like very spread. So they don't occupy a tiny parameter space. They are like very, very varied. So how do we know that they are associated to binaries? Well, the best example is this object, which was observed by Ogle's survey through all these years. It's high precision photometry. So then we saw that there's some brightening, a dip, which we still don't know what is it, and then a brightening. So the analysis of this part of the light curve showed it was actually periodic with some changes in shape that were similar to W or Ursa Majoris, which is like basically they are contact binaries which are actively mass transferring a sharing part of their envelope. The amazing thing is that the period of this system decayed exponentially through the years until we saw the outburst. So this was a clear evidence that in this case, we had a binary star that was orbiting every time faster and faster until it reached the merger. And we saw a luminous red nova event. So then we know that they are associated. And an interesting thing was that the donor was like 1.5 solar masses and a lower mass companion. And the donor was evolving off the main sequence. Aha. So why this? Well, let's look at these evolutionary tracks. This is a 5 solar mass star. It starts at 0 main sequence. During main sequence, it's burned hydrogen in its core. It reaches this point. And then when it finishes hydrogen, it starts to contract on thermal timescales. It's become a bit hotter. And then basically the layers of hydrogen, fresh hydrogen that are close to that now inert core, they start to have enough temperature to start burning hydrogen as well. So then we move into hydrogen shell burning, and then basically until we reach enough temperature in the core that we can go into helium burning in the core, and then we go to early GB. But then let's go to this other plot, which shows how the radius evolve with each stage. So main sequence, we see that the star expands just a little this contraction, on thermal timescales. And then this part is like, this is like a blink in the life of a star, right? You spend here like 10, 100, million years just like burning hydrogen and peacefully expanding. And then like, whoa, in a matter of a few thousand years, we have increased like 30 times our size. Then a small contraction and then increase again. So basically, this is called Hertzsprung gap, because if we look at the bunch of stars in the HR diagram, they're either in this part, like long-lasting, or this part, long-lasting. But nearly anybody is here because this is so fast, right? So now think about binaries again. If we have companions, and then we show that they had like, different periods, we can have companions like somewhere at this distance, or this distance, right? So if there's a companion, then you can start transferring mass during each one of these stages. So mass transfer during main sequence, case A mass transfer, case B mass transfer during this really fast evolution. And finally, this last one is case C mass transfer. So we can have different ways of transferring mass if we have a companion, depending on the evolutionary stage of our donor. So this is a little bit how the potential of two binaries should look like. This is mass ratio of 0.1, similar to B1309 SCO, which I just showed. So we have a deep potential well for the massive donor star and a tinier for the other star. This is a view from the top, and this is a cut here. So yeah, to exemplify, actually, I have here a 3D printed model. So I'm going to like just pass it on to the audience so you can like see in 3D how the Roche potential should look like. And I think that's a good idea to actually visualize with your own eyes this. But yeah, imagine this is our potential, right? When the gas is bound to the potential of the donor, it stays here, it doesn't go anywhere. If the donor expands, then the gas starts to kind of go into the companion through the L1, but then if the system even fills up more, then the next point from which the gas will spill is L2, and finally L3. And then you can see that in the 3D model. Okay, so this is kind of an analogy with water, right? Case A mass transfer would be something like this. It's a leaky faucet. You have something in your kitchen, you're bothered, but you put the bucket and everything is fine. You for the toilet, whatever you want, But then like what happened with case B? This would be something like this. If you have this in your kitchen, please run, because run for your life. Okay, so imagine like if you have a companion, this is your mass transfer. Usually it will be unstable, okay? Like the companion cannot accrete this, it cannot drink this water, it's too much, right? So binaries in this case, mass transfer will usually be unstable. All right, so let's go back to our Luminous Red Nova. From our archival search, we actually compiled the positions in the HR diagram of our progenitor stars. And we can see this is the main sequence, and the thin lines is actually this hydrogen shell burning. We see that the majority of our stars are actually in this regime. I mean, these dashed lines is like core helium burning, but like the majority of stars are kind of like sitting in here. I mean, this is main sequence, but it's debated as well, right? So, well, I mean, this is good news, because what we believe that these systems are like results of this common envelope evolution, their progenitors agree with the parameter space of where unstable binary configurations should be. So then one of the questions that we ask is like, if most of these progenitors are kind of these Hertzsprung gap stars, can we look in the archives in the Gaia, for example, to find stars that are now in active case B mass transfer? I mean, you saw it was such a fast process that detecting even like 1 or 2 stars would be already valuable, because we would be able to study much better like how this messy, holes is going through. So we selected stars from the Gaia catalog here, more or less in the Hertzsprung gap. They should have like some H-alpha emission, and the Gaia low resolution spectra here see a comparison, kind of H-alpha, it's still detectable here. They should be variable, because we know that like when you mass transfer, it's messy, you should be variable. Maybe are binaries, they have periods, and also we look for mid-infrared excess. Finally, characterize the Larry curve and spectroscopic analysis. So yeah, this was part of the Gerard, who is in the audience, PhD thesis. And the thing is, like, we selected them using one catalog, and then when we realized using spectra that they were redent stars, then actually they drifted into more like B parameter space, where it's like B stars that are rapidly rotating, likely accretors of binaries as well. Man, they're exciting, but we wanted yellow things, But I mean, we actually got, if you look at here, 3 candidates. Here we have an observed period for like sinusoidal or binary kind of shape slide curves. And this is the period of Roche-Rove overflow. So these systems are supposed to be Roche-Loeb filling binaries. So we found yellow stars that are likely in case B mass transfer. So this is an active project. Now we want to characterize like periods and radial velocities for these systems to fully understand if indeed they are actively mass transferring. Okay, so what else can we do? So let's see, from archival data, we determine the position of this progenitor star. And then we say, okay, well, fine. I have my single star evolution tracks. It's a Hertzsprung gap star. Okay, very good. But then if we say, okay, let's take one step further. These are binary stars. So then let's use detailed binary star evolution codes like MESA, to understand what kind of initial binary configuration can lead to this parameter space. Right? These codes are 1D, so basically they divide the star in layers, and each layer has its own like pressure, mass, luminosity, temperature, and then they make small modifications and they kind of iterate over the whole star, to reach the next kind of state of equilibrium. And through this process, you can actually strip stars, right? You remove a little bit of star. So what we see here is that to reach this progenitor parameter space, this is the main sequence track, the star is happy, it evolves until it reaches a companion. And then it starts mass transferring. And this is mass transfer rate. This is a lot. This is a lot as well. Right? So they already start transferring a lot of mass to their companion, and something interesting happens. Their luminosity drops. They are not like the stars they used to be. They shine less. So what happened? The star needs to readjust. It's losing so much mass. It's losing a lot of mass. So basically, it wants to regain its hydrostatic equilibrium. So it spends quite a lot of the energy generated by its internal reactions to actually reach this equilibrium. So you have less, basically, energy to go into radiation. So what we realized, actually, you can have like a centuries-long mass transfer from these systems, and the progenitor becomes a much fainter star. And this actually goes somewhere. So where does it go? Well, we believe that, if you are passing around the Roche-Loeb, there was the L2 point, which is the next point of potential after L1. So if you fill up enough gas in this binary system from the donor expanding, you start losing mass from this L2. And because the binary is spinning and every time faster, you can have like some sort of like spiral up that wraps around the system, and internal shocks can actually enhance the temperature in this kind of circumbinary disk that can contribute to some of the radiation that we see during the so-called precursor phase. So this is a simulation of B1309SCO that I presented before. This is the gas that it's lost through L2, and here the mass transfer rate. And here we see the shape of this binary that we would see if we are looking kind of sideways to this system. And we see that the gas that the small star is losing from the back, from the L2, is progressively obscuring this system. So then we start to see a change in shape. And this was seen in this system. So this is the precursor phase, and it's not only V1309 SCO, which is this one, but we see it in other systems, right? So every time we have one of these luminous red nova, if we have enough data in the past and the data is deep enough, we can look there and try to find this precursor emission, and we do see it, right? So then, like, the next question we ask is, okay, if all luminous red nova have it, can we predict the next luminous red nova based on this kind of slow and smooth rise? Well, for this, we had to rely on known data, right? So we assume that the progenitors of this luminous red nova will be these yellow supergiants. So we went on a quest in 369 galaxy with HST data to identify Hertzsprung-gap stars, right? The stars would be in this kind of yellow parameter space that are quickly expanding through hydrogen shell burning. So we got completeness for massive stars, you know, the ones that make all these neutron stars and black holes. And we looked also in time domain surveys what was the light curve of this source. So we identified 16 precursor candidates. Here you have like example of 3 of them that actually were yellow stars in the Hertzsprung-gap, and they appear to be smoothly increasing. So this is very exciting. We have a program at GTC which is ongoing to actually take spectra of these sources, first to know if they're generally yellow or they're like blue and reddened, but in case that, you know, we can actually study this binary system just years before the final merger. So this is very exciting. Okay, so what happens when they actually meet each other, right? This is a reminder, mass transfer, orbit, full envelope ejection, or a merger. So what happens is basically it's a transfer of the orbital energy of the companion through drag forces into the envelope of the donor star. And as you orbit inside, you get into a higher density and you go faster and faster. So this would be a kind of the analogy as if you want to make your favorite smoothie and then you forgot to put the lid, right? So the lid would be, you know, the power of gravity, but like here, you know, you have so much angular momentum so that everything just flies away. And this is what happened in one of these systems, right? Part of the gas just gets ejected. So, I mean, the smoothie analogy was great and all, but here you have actually proper simulations. This is a red supergiant donor with a 3 solar mass companion star. This is from the top. So just also pay attention into the distance between the 2 stars. You know, they started very far apart, and look where they are now. And I think this was a successful common envelope ejection. Like many of these simulations actually fail to eject anything, so they end up in a merger. So this is a side plane, and this is also a sideways, but it's like in a kind of rotating frame of the binary. Yeah, so the distance between the 2 stars has decreased by a lot. So we actually reached this channel, you know, to kind of join the stars through the ejection of the outer layers of the envelope. So what do we see? These are some of the light curves that we see. This is the days since the peak, the first peak, and this is optical luminosity. So we see a bunch of different morphologies. And if we look at the spectroscopic signatures during peak, it's very hot, right? So this is optical. So the peak of the emission is somewhere in the UV. We don't see, we just see these strong hydrogen lines. And like we also see these scatter wings, you know, this is basically when you have a highly ionized shell and there's like some energy source. So the photon have to pass through this ionized. So the electrons in this gas, they're actually bumping like or are taking energy away from this H alpha profile. So you have like a Lorentzian shape. So there's electron scattering here. And then like as you cool down, you become something like a yellow star. This is like sun-like G. And then at later phases, you start for molecules. So all these absorption is just like titanium and vanadium oxide, which means that the gas is very cold, right? Like you need to have a very cold gas to actually form and not destroy these molecules. So then this remnant becomes much redder than any supernova or any other transients that we can see. So these late phases is actually key to identify these transients as what they are. So this was 2020. Now, if we look at newer work, we can see that there's actually two emerging morphologies. So there is like something like a plateau morphology. There's a peak, a plateau, and a decay. And there's these guys, which we call the risers group, which have a peak, and then they have a rise, a second thing. So there's some theories about what this can be. So the plateau specially group would be more suitable for some modeling. There's like currently some analytical models which explain where the luminosity comes from. So in this case, we have this hot ball of gas, like the outer layer becomes neutral, it releases some luminosity, then this layer becomes neutron, and this layer and this layer. So basically it's successive layers that are releasing this luminosity as we go inward, and they power a plateau in these luminous red nova transients. Well, there is a little problem. If we go to very massive stars, so this is like 10, 20, and 30 donors, and here we have the ejecta mass that we need to power that plateau. Basically, this is one-to-one line. And we see that for a donor of like 20 solar masses, we require more ejecta mass to explain that plateau that it's in the star. So, I mean, this is not possible, right? So that means that something else is helping us to power this luminosity, and we believe that shocks have something to do. So here I would like to present you, this is like fresh out of the oven. This is work done in collaboration with Ondrej Peja at Charles University in Prague. So basically what we did is like, this is a mass transfer using these MESA models developed by Maxime, who is a PhD student in my group. So basically we see that this is the mass from the donor into the companion, and we see indeed that it goes kind of very nearly asymptotically up, right? So this is a runaway unstable mass transfer. And here what you will see is what happens to this gas, right? So if this gas is ejected from the binary, from this L2, and you also have the angular momentum of the gas and also the gravity of the binary and so on, what will happen? So this is the initial phases. We need to reach kind of some sort of like stable configuration, but as the mass transfer kind of increases, we can see that there's a huge mess here. So like, the gas falls down, it gets ejected, and it gets like kind of falls to the binary, return, and some of it escapes. But with time, we see that we actually are forming something like a disk. And this is like something like a disk. This is the density, so the higher density. It's in the circumbinary plane for this binary, and part of it gets ejected. Like actually, there's like some material like kind of piling up, right? I mean, this is a beautiful like butterfly shape. I love it. This is very pretty. But like I love that there is like a disk here. Because the previous simulation of this red supergiant that I showed you, in that case, we had a companion that just was kind of placed on the top of a spherical donor star. But this is utopia, right? Like what we have is this. This is the starting point of the simulation if we want to be realistic. This is the mess that you have when binaries transfer mass in an unstable ways. All right, so what we believe more is like, especially for the risers group, is that we have this slow precursor wind, that has made a disk. And when we have like a fast envelope ejection, this basically ejecta of this common envelope crashes into the pre-existing material, and there's like shocks. And this actually can help us explain these longer duration transients. So without interaction, we have a hot gas, it cools down, it goes down. But then if we have like some circumbinary disk at smaller or larger radius, we can actually extend and power this kind of second peak for these transients. And we can better reproduce the observations, which are kind of the faint curves. Okay, so what happens with the remnants? So it's very interesting because when we looked many years after the event, for example, 24 years after, like one of the galactic events with ALMA, which sees very cold gas, what we saw was like actually this, bipolar morphology similar to an hourglass. This is like a 3D reconstruction of this gas. So this tells us that indeed, maybe there was like something like a disk that actually shaped the fast ejecta into the polar regions. Yeah, so this is like kind of a cartoon to explain. We probably have some mass loss, which have shocks everywhere, with some pre-existing material. That could be some giant red star, which has more wind. There could be also jets and ambient gas, So, I mean, if anything, this is a mess, right? That just creates so much gas, Like I put the analogy, you have like a small kid eating some pasta, and this is like a nuclear disaster, everything got messed up. So basically, when you put two stars together and you feed one from the other, you end up with a mess, So then, like, what you need to do is evolve into this mess. So what do we observe? It's actually interesting because, the morphologies, this hourglass and so on, we actually see it, and this is a planetary nebula, which has this kind of hourglass, some kind of ring here. And inside here, there's two white dwarfs on a very tight period. These two white dwarfs, like 0.9 solar masses, when gravitational wave, takes off, like the angular momentum of the system, they will merge, and the sum of these white dwarfs will be larger than a Chandrasekhar mass. So this is like a very promising channel for making like double degenerate type 1As, right? And we do see short period corpses inside of these hourglass morphologies. So I mean, this is some also proves that these systems kind of deliver something that we see in nature. Okay, so the next thing we can do is also to estimate the dust yields. So we looked at some of these luminous red nova for different progenitor masses with James Webb, with my collaborators. And what we did is actually estimate the dust yields that each luminous red nova from each progenitor mass provided at a certain time since its peak eruption. And in this plot, you can see the dust map on the y-axis, and here is a core collapse supernova, which are supposed to contribute to dust production and the ISM. And here, the luminous red nova. We can see they start slow, but then they wrap up very quickly. These are very cold kind of expansions of the envelope, and because there's so much gas already there, it's so messy, that the new gas compresses the pre-existing gas, increases the density of that gas. And because everything is so cold, then you enhance dust formation. So basically, the dust formation timescales are very short. So this can help us, and this is very interesting because actually some studies show that there's too much dust in the ISM of the Milky Way. This is the Milky Way dust measured, and this is the contribution from AGB stars and AGB and supernova, but it says no reverse shock, right? When you have the core collapse supernova, you're ejecting part of these outer layers, but then this shocks the ISM, and then you have a reverse shock, and basically the reverse shock propagates inwards. So if you did form any dust in that ejecta that was expanding, the reverse shock will kill it. Okay, so then you will get actually this curve with reverse shock, more realistic. So then, like one of the solutions, if we think about binaries, is actually that binaries perhaps can help, to achieve higher levels of dust, because we have many systems in binaries: low mass, high mass. What do you want? Like half of the solar mass stars have companions, so they will become AGB stars. They may also eject envelopes, like this double white dwarf system that we saw. And also we have like higher binaries, higher mass, that also going to eject their envelopes. And because this is so peaceful, this is not a thermonuclear explosion, this is just kind of the ejection of the envelope. Any reverse shock, if anything, will be much, much smoother, and it will not contribute significantly to basically destroy all the dust formed in these systems. So I think we should work on this direction further to actually see if we can prove that binaries can help us achieve the same dust masses that we see nowadays. Okay, so I'm nearly close to finish, and here I would like to talk a little bit about the future. So the imminent future is Vera Rubin. This telescope, it's like 8.4 meter telescope. It's in Chile. And basically, the difference to other 8-meter class telescope is that its field of view, it's huge. This is the full moon, so it's 3.5 degrees across, so it's huge, right? And it's very deep. It's like 8 meters. So this telescope is making a survey for 10 years of the southern sky, looking for transients and looking for making like the deepest image of the universe that we can see in the southern sky. So this is great. We can see further, we can see deeper. The image quality from Chile is great. We all love it, but there's a problem. Actually, the forecast is that this survey will provide 10 million of astrophysical alerts per night. This is all great, but we don't want to look at 10 million of astrophysical alerts per night. We want to sleep, we want to do other things. So, ideally, we would love to see luminous red nova here, but we want to do something like 1 or 2 per day, so we can like get email, look at them while having the coffee, or like discuss them in the group meeting. I don't know, something like that, right? So what can we do? Well, we need to solve these problems. So some of our solutions that we came up so far is actually to compile something to compare to, right? The first thing that I mentioned is that if we think or we believe that the progenitors of luminous red nova are yellow supergiants, we can use a catalog of our HST 200,000 yellow supergiant stars to cross-match with LSST alerts. So anything which is yellow and it's increasing in brightness, we will look at it with lots of care and love, because it can be like a advertisement that a luminous red nova will happen in a few years. And on the other side, as I mentioned, luminous red nova are gap transients. So we want them to be in this luminosity gap between novae and supernova. And how do you do that? You need a distance, right? So for that reason, we also compiled a catalog of 80 million galaxies up to 2 gigaparsecs. So basically, we can cross-match with incoming alerts and identify those that are in between. So there are not that many of those. And finally, we are now working on developing statistical methods and machine learning for classification of light curves. So even if we don't get kind of too many candidates, we are going to be able to actually apply some statistical methods to deliver 1 or 2 per day. So yeah, the idea is like on long term, with all this machinery in place, LSST will allow us to not study individual events, but a whole population. Right? So we can actually study which populations of binaries become unstable if we have reference surveys like Euclid right now, or Gaia, or, well, yeah, Rubin itself will also provide a baseline. We can actually see also the progenitor stars. So we can characterize them. We can see a luminous red nova. We know that they were unstable. So we will be able to characterize all the unstable binaries that we detect here. And yeah, just to conclude, I hope I convinced you. Binaries are important to understand the unity of the universe. And luminous red nova are key elements, right? All these processes that we don't understand so well, we can use them to try to shed light on some of them. For example, like centuries before and years before, we can try to identify their progenitors, study which binaries can actually give place. We can study their precursors and try to simulate those systems to understand how mass transfer is wrapping up and what's the mess that it's resulting. Then we can look at their light curves. We can understand better what's happening in this common envelope ejection process, how much mass is ejected, what energies are important, recombination energy, orbital energy, or others. And then we can also look at how the remnants evolves, what are the geometries, so that we can actually match them with existing stars or stellar systems that we identified now. And finally, from here, we can also be able to infer better the physics of binary evolution, so we can constrain better the rate of these neutron star mergers that are important to make the elements that are essential to our life. Thank you.
Thank you very much, Nadia. Very well on time, and very interesting and clear talk. Also funny to some extent. Thank you. So there is time for questions, comments.
Yeah, I have my master's students there, so I know I have to entertain them. Otherwise, they get on their phones and, yeah, they don't listen.
Young people, yeah, terrible. Okay.
Yes, thank you very much, Nadia. That was really nice. So you mentioned towards the end something actually planned to ask, so maybe I shouldn't yet, but could you maybe already say something about how much constraint we can put on rates from the observations you have, and how much the common envelope plays a role in the binary black hole formation? You know, in the community there's a big discussion about the relative importance of stable mass transfer versus common envelope. I mean, or do we really have to wait until Vera Rubin before we get the statistics to do
No,
that?
I mean, what we need is to do binary population synthesis models, and this is the next step. So yeah, I have a 5-year grant, so the 5th year would be devoted to that. So the problem is like we needed a bigger, relatively bigger sample. Now we have 30 objects. We can start defining some correlations between light curve properties, progenitor properties, and then basically we can use this to simulate large populations of binaries, right? And we can input different physics for common envelope, like how much is ejected, how much is preserved. So basically we can test different prescriptions. So I think we can do something now. Of course, with Vera Rubin, this will be like a whole new level, factor of magnitude more of objects, but we should start now. So yes, the plan is like for next year, for example, to start experimenting with different binary population synthesis and say, if we simulate 10 million binaries using these physical assumptions, do they agree with observations? If we change our assumption and we simulate another population, do they agree with what we observed? So we can start putting some constraints on that, yes.
If nobody else asks a question, then I'm going to ask a question that may sound either provocative or open-ended, depending if you see the glass half full or half empty. So when you talk about Vera Rubin LSST, and you say that there are 10 million object events per night, of which you expect, I don't know if you want or you expect.
That's the prediction the LSST team gives.
Exactly, so you just take that. And this is a problem that is quite generic whenever you enter in the big data regime, and our particle physicist friends know that because they use triggers all the time to actually detect only the event that they're interested in. You put basically some selection at the very beginning. You throw away a lot and you keep only the things you're interested in. Don't you have in the back of your mind maybe the doubt that you may be throwing away things that may still be useful just because you can't deal with otherwise you can't find the needle in the haystack, and so all your needle end up looking the same because you know what you're looking for? Is that a concern, or in this case is not an issue?
Yeah, I mean, it's an interesting question, right? Because if you're flooded with so many alerts, in my opinion, you have to have a very defined science case so you don't get lost. Once you have completed your project, I think it's very interesting to do what you said, right? You just say, okay, I'm going to be an open-minded, I'm going to let the machine learning algorithms tells me what's in the data. But I think from the point of view of this luminous red nova, for example, sometimes light curves are not enough, so we need spectra. And if you want to focus on like having a follow-up from ground-based telescopes, you need to really like focus on some particular events which are rather bright, and they have maybe progenitors known, so you can enhance the science that you do with them. Then once that is done, like of course you can do an archival search and say, I'm just gonna like try to find more of this luminous red nova. The problem is that the cadence of SST is not wonderful, and they also are going to be very distant. So then, I mean, this is going to be a probabilistic classification for this object. So then you are entering, as I said, like the big game data, so then, well, it's different science that you can do, and it's actually, I think it's complementary.
Yeah, thanks for the talk. You showed these outflows that you have in some occasions. What is the velocity of the outflows? And I don't know if you mentioned that. And is there any possibility to constrain the energetics? And would this help to constrain the problem at some point?
Yeah, actually, I was wondering about the velocity as well. I mean, this is work by my collaborator, which was like finished a few days ago. So Yeah, I didn't have time to actually look at this, but yeah, I mean, that would be interesting, because then that would allow us to compare with observations, because we do see absorption from cold gas at given velocities. So then if these outflows having like comparable velocities, that gives us actually more clues that the system that we are seeing had some precursor phase as messy as this. Yes. But I would say hundreds of kilometers per second range. Exactly the numbers, I don't know, but like not more than that.
Okay, thank you. So yes, I wanted to ask about the population of white dwarf binaries. So it seems that from your studies, you can learn a lot about this. And this, of course, will be very interesting for Lisa to know, just studies of population of how many white dwarf binaries we have as a function of several parameters, right? So what do you think about this?
Yeah, I mean, the problem is that white dwarfs would come from low mass systems, and there is a luminosity of this red nova versus the progenitor mass, so that the lower mass system cause very low luminosity events. So then they need to be in the Milky Way. And in the Milky Way, we have like 5 luminous red nova for the last 30 years. So then like basically we need to go outside of the Milky Way, at least M31 or further. And that makes us to go to like higher masses, basically. So let's say with these systems, we have less information about lower mass, because they're low. They're too faint and we don't see them. But yeah, maybe with Rubin, we actually will detect low mass, systems in M31 or somewhere nearby. But the physics should be very similar, actually. So what you can infer from one should work for the other one.
Time for more questions, comments. If not, I have a question myself. I'm not sure. I want to give you an example, and I would like to know if it makes sense, okay? Because it's related to something I'm working on. So is it possible to have a pretty large mass, quite massive star close to a companion, and to have such an efficient mass transfer, then you end up with, you initially have something maybe, I don't know, maybe 20, 30 or more solar masses, and you transfer so much mass, then you end up with a white dwarf in this primary star, while the secondary star becomes quite massive.
Started with 20 solar masses.
So you have this primary, which evolves faster, and it transfers a lot of mass to the secondary, and it's so efficient transferring this mass that before it can collapse or something or merge, the primary core, you end up only with I don't know, 1 solar mass or something like this. So basically, you just have a white dwarf, while the companion has become, much more massive. Yeah. Does it make sense to you from your from what you know?
Yeah, that I guess would be case A mass transfer, because you kind of removed so much mass. But yeah, generally, like you would make most of your evolution after like hydrogen core burning, and then it's the core mass which determines your future evolution. So then that the stripping would need to happen like way earlier. So yeah, I think that would be a very kind of targeted evolutionary path, not very standard, I would say.
Very unlikely.
Yeah, unlikely. Yes.
Okay, thank you. Any more question, comment? If not, let's thank again Nadia for this very nice.
Thank you.
Let's close here. Thank you.